Good day. Let's now talk about Lesson 2, Current, Resistance, and Electromotive Force. In the past lesson, we've studied the interactions of electric charges at rest. Now we're ready to study changes in motion. An electric current consists of charges in motion from one region to another. If the charges follow a conducting path that forms a closed loop, the path is called an electric current. So fundamentally, electric currents are a means of conveying energy from one place to another. As the charged particles move within a circuit, electric potential energy is transferred from a source such as a battery or generator to a device in which that energy is either stored or converted to another form, into sound in a stereo, or into heat and light in a toaster and a light bulb. Electric circuits are useful because they allow energy to be transported without any moving parts. They are at the heart of flashlights, computers, radio, television, transmitters, receivers, our laptops, and our cell phones. Your nervous system is also a specialized electric circuit that carries vital signs from one part of your body to another. So in this lesson, we will see how to analyze electric circuits and will examine some practical applications of circuits. Before we can do so, however, you must understand the basic properties of electric currents. And these properties are the subjects of this lesson. We'll begin by describing the nature of electric conductors and considering how they are affected by temperature. And we'll also learn why a short, fat, cold copper or copper wire is a better conductor than a long, skinny, hot steel wire. So, yung mga light natin sa bahay, merong maninipis at merong makakapal. In this lesson, we will learn bakit yung mga makakapal na copper wire is better than doon sa mga thin wires. And also, we'll study the properties of batteries and how they cause current and energy transfer in a circuit. In this analysis, we will use the concepts of current, potential difference or voltages, resistance, and electromotive forces. So, the focus of this lesson is about the current, the potential difference or the voltage, the resistance, and the electromotive force. Ano ba yun sila? If you look inside your TV, your computer, or under the hood of a car, you will find circuits of much greater complexity than the simple circuits. Whether connected by wires or integrated in a semiconductor chip, these circuits often include several sources, resistors, and other circuit elements interconnected in a network. We study general methods for analyzing such networks, including how to find voltages and currents of circuit elements. And we'll learn how to determine the equivalent resistance for several resistors connected in series or in parallel. So from the previous discussion, the series and parallel connectors are all about the capacitors. And now we are talking about the resistors in a circuit, whether it is connected in series or in parallel. So we'll discuss instruments for measuring various electrical quantities. As for the learning outcomes, at the end of this lesson, you will understand the meaning of electric current. You will visualize how charges move in a conductor, and also you distinguish what is meant by resistivity and conductivity of a substance. Calculate the resistance of a conductor from its dimensions and its resistivity. Explain how an electromotive force or EMF makes it possible for current to flow in a circuit. Solve calculations involving energy and power in circuits. Analyze circuits with multiple resistors in series or in parallel. And lastly, understand the uses of an ammeter, voltmeter, ohmmeter, potentiometer in a circuit. So, learning content 2.1, current and current density. A current is any motion of charge from one region to another. In electrostatic situations, like discussed in lesson 1, the electric field is zero everywhere within the conductor and there is no current. However, this does not mean that all charges within the conductor are at rest. In an ordinary metal such as copper or aluminum, some of the electrons are free to move within the conducting materials, because we have discussed what is in the copper or in aluminum. There are free electrons that are free to move within the conducting materials. It is interesting to note that a current carrying wire is not electrically charged. Under ordinary conditions, negative conduction electrons swarm through the atomic lattice made up of positively charged atomic nuclei. So there are as many electrons as protons in the wire. Whether a wire carries a current or not, the net charge of the wire is normally zero at every moment. In different current-carrying materials, the charges of the moving particles may be positive or negative. In metal, the moving charges are always the negative electrons, while in an ionized gas plasma or an anionic solution, the movement charges may include both the electrons and positively charged ions. In a semiconductor material such as the germanium or the silicon, conduction is partly by electrons and partly by motion of vacancies, also known as holes. And these are sites of missing electrons that act like positive charges. So kung maalala nyo yung ating semiconductor sa previous topic, merong mga holes. And that holes will be the site for the missing electrons that will act as the positive charges. Now, in this lesson, for this figure 2.1, the same current can be produced by positive charges moving in the direction of the electric field. These are the positive charges moving in the direction of the electric field. Where is the direction of electric field? It's into the right. Okay, so in this figure, the same number of negative charges are moving at the same speed in the direction opposite to electric field. So, why is it na si positive charge will go to the direction of the electric field while si negative charge will go opposite kay electric field? So, this is mainly because ang ating current is kung saan si negative, doon si current. And kung nasaan si current papunta, doon si electric field natin. So, ang ating electric field is moving to the right, and into the right is the negative terminal of a voltage source. For example is ang ating batteries or ang ating current. Kung saan si negative, si current natin is flowing into the negative. Okay? So, ang liban lang is, si positive charges will always be to the right kasi attracted siya kay negative terminal. So, this is why si positive charge is moving in the direction of the current, where si negative charge is moving opposite kay electric field or opposite kay current because it is attracted to the positive terminal. Going back, so figure 2.1 shows segments of two different carrying materials. The moving charges are positive and the electric force is in the same direction as the electric field, and the drift velocity is from left to right. So, in-explain ko na yan. Again, si current is papuntang right. And si electric field is also papuntang right, and also the electric force. Bakit? Dahil sinusundan nila kung nasaan si negative terminal. Now, we describe currents as though they consist entirely of positive charge flow. So we will describe current using the positive charge flow. Okay? So, kung saan papunta si positive charge, doon papunta si current. So, si current flow natin is also the positive charge flow. Even in cases in which we know that the actual current is due to electrons. 'Di ba? Electrons yung nagmo-move sa ating element, sa ating mga copper wire. But in this practical convention of current, dinidescribe si current as positive charge flow. Hence, the current is to the right in both the figures, and this choice or convention for the direction of current flow is called conventional current. Okay? Now, we define the current through the cross-sectional area A to be the net charge following through the area per unit time. So, current I is equals to the derivation of Q, or derivation of charge over the derivation of time, or simply charge over time. SI unit of current is ampere, and 1 ampere is defined to be 1 coulomb per second, or 1 coulomb per second. This unit is named in honor of the French scientist André-Marie Ampère. André-Marie Ampère is a man na kapangalan niya ay babae. So, let's continue. When an ordinary flashlight is turned on, the current in the flashlight is about 0.5 to 1 ampere. The current in the wires of a car engine starter motor is around 200 ampere. Of course, sa ating car, kailangan ng malaking amount of current compare kay flashlight. So, currents in a radio and television circuits are usually expressed in milliamperes, or 1 milliampere, or 10 to the minus 3 ampere, or microamperes. That's it. And current in computer circuits are expressed in nanoamperes or picoamperes. Suppose there are n moving charges particles per unit volume, and we call the n concentration of particles. Its SI unit is m to the minus 3. And assume that all particles move with the same drift velocity with magnitude Vd. The current per unit cross-sectional area is called current density. So, ang kaibahan lang nila, si current density is dependent siya kay area. And what is the area? Area of the wire. Okay? So, ating copper wire is area. Ang area niya is, punta tayo sa figure, ang area ng ating wire is pabilog. So, that is a circle. So, that is area of a circle is 2 pi r squared, or 4 pi d squared. So, pi d squared over 4, or pi r squared. Okay? Next. Hence, the current I and the current density J can be expressed as I is equals to the concentration, the charge, the drift velocity, and the area of the wire.